young, I was dumb then. Running wild, low in self-esteem. Girl, you were everything I didn't need. But I think that's probably why we never got that far. Making out in my broke down car. Tried to change me, I was too far gone. But can't you?
Everyone gets a 2-hour average in a year and still hits 5 nights.
All right, let's try to get started.
What are you offering? I don't know.
So a few minutes, there might be people showing up. I'll go let people in, but we'll kick it off and then not waste anybody's time. Thank you for coming. If you're here, hopefully you're here for the meetup. If Gopher on the screen hasn't keyed you into that, then I can't help you. Quick warning: the recording probably won't pick you up anywhere because it's gonna be a lapel mic this time, but anybody online will be able to hear you through these little boxes above your head. They're very good microphones that will zero in on your whispers, and the people online will know all your secrets. if you want to come speak here, we are out of talks for the rest of the year, to be honest. It's all wide open going forward.
Wrong year, you need to update your slides to 2026.
I want to. It's 2024.
Okay.
So we got the whole rest of the year open. Got another 6 more months of talks to fill. I'm still looking for. We've got tons of standard lit. So very thankfully we've got a talk about the crypto packages, which I wasn't sure anybody's going to do. Like there's some standard library packages that are esoteric and weirdos like we care about. But there's also a bunch of other ones that are not so esoteric. There's like nobody's talked about FUMT yet. Like someday, hopefully this year, we're going to come talk about FUMT. I guarantee you there's stuff in there that some of us don't know. So I'm encouraging you, please just you can submit through here. You can come talk to me afterwards. You can go to forgeutah.tech, join the Slack, go to the Gophers, say, hey, I want to talk about the standard lib. Specifically in that channel, in the canvas in that channel, which is kind of their wiki that's attached to the channel, we have a big list of all the packages and kind of grouped up into logical units that I think make sense. Go through there, see if there's anything that you're either know a lot about or want to learn about. And there's so much that comes built with Go. And people really take into this kind of like, let's just talk about the stuff that's in the language. Like we don't need to get fancy. We don't need to even talk about third-party libraries or really fancy tools people are building. Like let's just like what we just get with the language for free, which is really significant with Go. So that's how you can come speak here. I always take a second to point out the jobs channel on there. It's been refactored recently, so if you haven't rejoined that, it's now kind of more well structured. The jobs channel now has this like formal submission process where it breaks out stuff into specific sections, so it's way easier for you to parse as somebody looking for a job. It's actually processed data instead of just randomize people's postings. So go check that out, or post there if you have a job. And you just click a form and fill in some boxes, and the job there just as easy. Go West. I've been told that the tickets are not yet available, but they're going to be available very soon.
And Derek's on it right now.
Nice. So Derek's on it. You can go to gowestconf.com. That is a local Go conference that is held here at Weave. Really fun if you've never done it. It's super affordable. It's local. It's a blast. Like done it every year since we've had it, and it's always fun. Yep.
Speaking almost every year.
Yeah, I do that too. So it's a lot of fun. I highly recommend people come to Go West and hang out for the day and learn a lot about Go. That's it. I'm gonna pass it over to Steve. Steve's gonna talk to us about the cryptography. So again, esoteric packages for weirdos like us.
Yeah, exactly.
Yeah, thanks, Steve.
Okay, so now I can share this screen. Entire screen. There we go. And I'll just slideshow. Okay. Yeah, so my name is Stephen McFarland. I work at a company called Scientist.com. Our main app is a really old Ruby on Rails app, but I was mostly self-taught in how to program, and so I still like to do it as a hobby, and Ruby feels like work, so I like to program in Golang on the side and wherever I can sneak it in. And then a little bit about the scope for this talk. There is a lot in the crypto package. Some of it is completely irrelevant, which I'll show later. So I'm mostly going to give a high level of how you could use symmetric and asymmetric crypto as you might need to in whatever application you're writing. So first, like why crypto? Where is it relevant in software development? And it sneaks its way in just about everywhere. It's all over networking because you really like to hide what you're sending from middlemen so that just people on the ends of the connection get to see what you're sending. We also encrypt things at rest so that data is protected from unwanted eyes. And then a final use of crypto that we use a lot is for data integrity. So we know what someone has received is exactly what was intended to be sent. So these are various things you might use the crypto package for. So then why use the Go standard library crypto stuff? The main reason is you never write your own crypto. You never write your own crypto. Again, you never write your own crypto. Yes, everything's published. You can figure it out. It's all there. But using standard approved vetted packages for crypto is very important to know that you're getting the best bang for your buck and accurately implementing what you intend to implement. This is also why I won't use Telegram, because they implement their own crypto. So, a little bit of foundation. Crypto really depends on actual randomness. That said, computers are really bad at random on purpose. We usually intend for our math, what we display on the screen, everything we do to be repeatable and accurate, which randomness is the opposite of that. That said, Go provides a way for us to get as random a values as we can get using Rand Reader, the Rand package from the crypto package, and you'll see it used in all of my examples because randomness is critical to make sure that what you're encrypting can stay secure. It is hard for someone to take a known state ahead of time and reverse engineer your key and decrypt your stuff, but it has been done. And there's lots of stuff littered through the history of crypto of failed algorithms and failed methods that to a large part failed because of how they were using randomness or didn't have randomness. So the first kind of crypto I wanted to talk about is symmetric key crypto. It's called symmetric because you use the same key to encrypt data and to decrypt data. This is the same thing as like a shifted alphabet cipher you did in elementary school, where it's all the letters shifted 3 over in the alphabet, or you used a scrambled alphabet cipher. You encoded a message, you handed the key to someone else, they could decode your message. It's the exact same thing. It's good because it's fast and efficient, but that is that challenge of, particularly if you want someone else to be able to decrypt your data, they need the key and you can't just hide it. So you need a good way of getting them the key, which we'll get to later. Now I want to get a little bit into the weeds here, but not too far, just to get a bit of foundation. The algorithm I picked for this talk for symmetric key crypto is AES. If you bought a product or software and it says military grade encryption, this is all they're talking about. It's the standard for symmetric key encryption. It's called a block cipher, where it encodes in blocks that are the same size as the key length. And it uses multiple rounds and lots of tricks to really scramble the data, and it is really secure. That said, just to dig a little bit deeper, one thing you'll see in all these examples is just the algorithm is not enough. The history of crypto is long, and we've learned that we need to use the fancy math in the correct way to avoid attacks where our data could be decrypted. So the example here for symmetric key crypto is we use this thing called the Galois counter mode, and there are several of these, but this is a good one to pick, that in addition to encrypting all the chunks, it connects them together. It makes it easy to encrypt a large chunk of data. It also adds validation for that data, which is really handy so that you know you can decrypt and it is the data that was sent. So let's look at some code. Let's see where to go. Here. So here's the crypto packages this is using. So we have AES, we have Cipher, which is where the mode comes from, Rand, because like I said, you need randomness. So for AES, let me make this a little bit bigger. I don't know if you can, it's kind of big. We have to have a key of the specific length required for what we're doing. So in this case, In this case, I need a 256-bit key. So for my example, which you'll see in a minute, I let you just put in whatever passphrase, but I need it to be 256 bits. So just using a simple hash to turn that into 256 bits. And then to encrypt, you get a new cipher struct, and then you pass it to, here's where that mode comes in, GCM. We pass it to that, and then here's where randomness comes in. We need what's called a nonce, or a number only used once. This is a bit of randomness that GCM uses to ensure everything stays nice and tidy and encrypted. And then finally, it's easy just to use the seal method to get your ciphertext. And as you'll see a pattern that emerges, decrypt is just the opposite. We do basically the exact same setup. We get our cipher. We set up GCM. To get our nonce, GCM appends the nonce, because we need the same one, to the end of the ciphertext. So here we're able just to slice it off the slice.
So we
And
have to have the key and the nonce sent over somehow in order to decrypt this?
yes, so the key you would send some secure way, probably public key crypto, which I'm going to talk about in a minute. But the nonce is the format of what GCM gives you at the end. It's always appended to the end. So it's sent with the ciphertext. And the key you send securely some other way. And so then the open method here will give us our plain text back. So let me get rid of that in the middle.
So the nonce is also 256 bits, right?
I forget how big it is. If you look at my example again there, it tells you exactly the size it should be from this cipher struct. So that's the nice thing about Go standard library for these things. The values are all just there. They make it really easy to figure out what you need to use, because it does need to be a specific length, but I don't have to care because I know if I use the nonce size method, I get the right size. Okay, let's come back here. So here's a little example where I compiled that Go code you just saw to WASM so I could play with it in a web site. And I can give you these URLs at the end, and you'll be able to play with this if you want, because I've found playing with encrypting and decrypting values is a good way to mentally lock in how this works. So here I have a bit of text. I can encrypt it. You get base 64 gibberish, and I can decrypt it. But if I get my key wrong, something else in there, and I try to decrypt, I can't. Message authentication failed, and I can't decrypt. So it's pretty straightforward. Where you would use this would be you need to encrypt a file, or maybe you're encrypting specific fields in your database that you don't want to leave in plain text. Anywhere where you don't want anyone to see things and just specific people, you can use symmetric key crypto. Okay. Now, public or asymmetric key encryption. This one is generally a bit trickier to understand because you have two keys now that perform separate roles. One key is always kept private and you do not share, and one is public and you give out to whoever might need it. So the first example of how you would use it is you want someone to send something to you that is encrypted. So you hand out your public key to whoever that might be, and they can encrypt that value. Once it is encrypted, only the private key that I have can decrypt that. So that's where, say with symmetric key crypto, that's faster what you'd want to use most of the time. So you can use public key crypto to securely send the key to someone else. So then you can exchange data over using symmetric key crypto, which is a lot faster and a lot more efficient. The other use of public key crypto, the way I think about it, is it swaps the places of the key, and that's how we can get validation of data and signing data. So you still have a private key and a public key. What I would do is I would use my private key to encrypt a chunk of data, usually a hash of something, and then I can send that data and my public key out to whomever. And only that public key can decrypt that value. So you can use that to know that I encrypted that hash. So if you do the same hash of the same data and you get the same value, you know that you have exactly what I intended to send you. Let's see. So to get into the weeds again, a couple of algorithms that are used here. RSA is the tried and true, using prime factorization as the hard bit of math it uses to do public key crypto. And then the other one you will see is elliptic curve algorithm. And to avoid making this talk go for too long, you'll see at the end of the methods in the example for these, an acronym again. Again, you have the algorithm, and then you have a way of using the algorithm for a specific use case. And so whenever you have time when you are going to be using this, it is always good to do a bit of research to understand what algorithm is the one you should choose and what method of using it works for your application. Because it changes slowly, but it does change over time what you should use. So back to some code. Let's go to, so here's my RSA example. So first we need to generate this public-private key pair. In this case, here, this you see we're using rand reader again because we need to use randomness to generate our key. You can store this key in whatever method works best for you. If you just want to hex encode it or base64 encode it. In this example, because it is commonly used, I'm turning it into the PEM format, which if you've interacted with services and needed to exchange keys, you've probably seen PEM formatted keys before. So then to encrypt, we need the public key. And then here's just the decoding of the PEM format. And then it provides, the library provides a way of checking that it is a valid public key. And then again, it's a simple method off the RSA package to encrypt. So it needs a hasher, a bit of randomness, a public key, and your plain text as bytes. So again, always randomness. Then you get ciphertext. Mm-hmm.
What's that? This at the top in the JS package. That threw me for a loop.
It's just pretending you're in JavaScript.
Okay.
You don't have to, you can name it whatever you want. It's just when this is being compiled to WASM, a little bit of a reminder that you're kind of playing in JavaScript land is helpful.
So how are you using the this? Is it used all in the code here, or? Oh, I see.
Yeah.
Okay, so that's just your input.
So that's just the input that's needed. And then the args is what really matters. Yeah, the WASM stuff is just, I just followed along because it's easy enough to make work, but I wouldn't probably use it in production. It all feels a bit janky and it requires a special library you have to dig out of Go where it installs it.
Because yeah, I've never even started. I'm really fascinated that at the top, the import for that was like not a package. That's syscall
So
JS.
so that's part, when it compiles
Mhm.
to WASM, it's actually using JavaScript, the JavaScript compiler.
Yeah, and there's this JavaScript file you have to use with the Go compiled WASM that I think like it has like a JavaScript version of malloc in it. Like we're getting into weird territory.
Because it's
It
using.
is syscall stuff.
Yeah, so you see all this syscall kind of stuff, but defined in JavaScript.
Okay.
That's how Go works with WASM at the moment.
That's okay. No, that's fine. I haven't done much Go to WASM, so that's why that looked so new to me and it was so
And when
bonkers.
you do your Go OS for the compile, like your
Yeah.
JS, not WASM.
Okay.
So it's like.
It's cool, but it's bonkers.
Yeah.
Okay. Sorry, that was.
And well, then the decrypt is really just the exact inverse, where you just use the private key. I have the ciphertext base64 encoded, and then we're able to get the plain text out using basically the same function signature as encrypt. Everything's kept nice and consistent. So let's see if we can go to my RSA example and I can refresh. So you can generate keys. So this is the PEM format that you may have seen before, where it has the header and the footer with all the random gibberish in the middle. So I have our message, and similarly you can encrypt it. You use the private key to encrypt it, or the public key to encrypt it, and then the private key to decrypt it. And then I have one more example. And this is for a signature. So this one, just to use something different, I used an elliptic curve algorithm, but it's very similar, and you can do the same thing with RSA, and it would be fine. So in this case, again, we have to generate our public and private key. We marshal it to bytes, and we encode it as hex, because that's easier. And then to sign message, so like I was saying before, you use the keys slightly differently, where we're using the private key here to do what feels like encrypting, where we're signing the message. And then we get a hash, because part of the reason you use a hash is not only is it easier, but public key crypto is expensive on compute. So the smaller the value you operate on, usually the better. And since a hash is, you throw data in, you always get the same thing out, you might as well use a smaller bit of bytes. And so then the ECDSA package has a sign method. Again, the sum acronym, that is the mode that's used for how this signing is happening. And again, you always have to use some randomness. So at the end, we get a signature. And then to verify, as you've seen the pattern, it's the exact opposite. Where in this case, we're getting the public key, we're getting our hash, and then we're using the verify method with our public key, the hash, and the bytes from the signature. And we are able to tell if it is verified or not. So then I have an example for that too. So you generate the key pair, and then when you sign the message, you can verify it. So it's valid because I haven't changed the data. But if I change it now and try to verify it, it's invalid, and I know the data is different. Okay. Let's go back to the slideshow. So, notes about the future, and if you decide to implement this, quantum computers are theoretically coming sometime, 20 years maybe. The biggest prime number that I know it's been verified that a quantum computer has been able to factor is 35. So, it might take them a little while, but it's...
This is one that they'll tell you about.
That they can detect.
Yeah, the...
Research paper that
they could factor 22-bit RSA.
Well,
It
they,
hasn't
they
been independently verified.
and they well, even in the paper, they kind of cheated where they're only doing silent kind of the last few bits.
See?
So they're working on it.
Someday.
I mean, the NSA is vacuuming up all the data it can, so they're hoping they can decrypt later. So it's good to think about potentially using new, more secure algorithms. And Go is already working on it. Of course it is. So there is the algorithm. The MLKEM is one of the quantum resistant algorithms they have in here, as well as there's more under the X crypto packages where new experimental stuff is coming in. So in here there's stuff like Argon 2, which is supposed to be crypto resistant version of bcrypt, and all kinds of new stuff in here. And then I also just wanted to reiterate, always do a bit of research before you pick what you use. Because, for example, there's stuff that is in the standard library that you should not use. And it says so. DS is cryptographically broken and should not be used for secure applications. It's here for legacy reasons. It'll probably never be removed. But there is so much available, and so many of these algorithms and ways of using them are use case specific that it's good to put in the research first to know what works for your application. And I think that's it.
I think it's cool. Just to like reiterate some practical stuff from the talk. Like what that means is you've got back on. You've got infrastructure as good as that's what services, and you want them to securely send the like built into the language with some minor stuff. You've got the ability to give a secret to one side and the other. You can do this in any language, but that those languages have some of these. Like if I'm gonna like narrow down what's cool about this and Go is that it's a lot. That's a lot. That's a lot of like there's very few things that it's like, oh well, our platform uses this kind of encryption. We're like, well, we're in Go. We don't really have an implementation of that. Like that might be the coolest part about this is how broad that standard lib is for just like, yeah, all of them are built into the language.
And some other stuff that you use normally every day, like TLS, it's using all of this under the hood, which is part of the reason why it's implemented. If they're going to implement TLS, they might as well implement all the stuff that TLS can use.
Do you know what type of randomness is being used in WASM? I'm just curious because I know there's like a difference between dev random and dev u random if you're on a Linux system and what guarantees they try to provide.
I would not trust this given it is in WASM because it is using the JavaScript VM and they deliberately limit the amount of randomness that it's like, don't write a secure service in Node. You can't, V8 doesn't give you what you need because that's not its intended place to be used.
The random algorithm just trips them.
You can't get precise time in JavaScript. You can't get really good randomness.
That said, the package itself, if you are not in WASM, is actually very clear on what specific sources of randomness it will go to in order on each system, on each platform.
And so it starts with the good one, and then if that gets exhausted,
Yes.
And most operating systems like provide this, like you need good randomness.
Not WASM.
All right. Anybody have any other questions? Oh, I have one. Should I write my own crypto?
Oh,
You
But-
should. You absolutely should.
What if I think I know better than the Go containers? What if I use an agent
they hire
and
someone.
vibe code it?
especially, no, I think you should. I really do. Like, I think everyone
It's something to learn.
should take a moment and implement like one of these algorithms themselves. Not use it in production, but to learn what the hell goes into it and just how few test cases there are. Because you kind of like I've implemented SHA-256 from scratch because C# at the time did not have that in its core libraries. So there are 3 test cases in the official spec. It is not exhaustive. They are mostly bullshit, and it was a great learning exercise. The key here is like once you learn that they're not scary, you actually learn more about why you do want vetted and secure third-party implementations at a level that is not just a talk like quip on a slide, but like you could actually talk about like, no, this is exactly where and when I would implement my own crypto and why I would avoid that like the plague, why I couldn't do that, and why the vetting is actually the more important part because we've all agreed that this is the right spec, even though nobody has any proof of that. We all use it, it's fine. And so like there's lots of nuances there that you get from just literally just one of these. Go and do it. It's such a wonderful.
It's a fun little project to go try and do.
I did the same thing with Jot. I implemented like my own Jot, and I spoke about it here, and it made me 1,000 times less afraid of not just Jot, but like several other like off concepts because I got exposed to like I would never use that library that I wrote in real, but by implementing even just a basic one, I'm like, oh yeah, none of this is that scary.
Yeah, I mean,
learn math though, which can't be scary.
yeah, and you'll learn like a lot of deep computer science, XORing, bit shifting, like a lot of stuff that you're just gonna like, oh, this is just random stuff that they put in the spec of like, this is the bytes you start with. Why? Because like, and it doesn't take long. Like SHA-256 took me an afternoon, and then I spent another entire day generating 1,000 test cases with like 3 other tools to make sure that they all matched.
Oh my God, do it.
Yeah, just don't do it in production.
So, when you're converting a
password into your key, how does your hash work? So like you're trying to develop something random, right? So if you actually fill in your password, which is like 8 characters long or even 16 characters long, you have half of your fields that turn out to be 0, right?
Yeah, I'm using SHA-256. So that's whatever bits go in, you get 256 out that are random gibberish, but 100% directly connected to the bits that came in.
and also guaranteed to be unique, asterisk.
Yeah,
Guaranteed to be unique,
practically,
like getting struck by lightning 40 times in the same day, kind of, maybe.
So the problem with that is like a lot of people who use, like, even if you use these algorithms, if you apply them wrong,
Yes.
you're like dead in the water, right?
Uh-huh.
Like there was a company, it was actually Google, I think, in their early
Number or something. And then they encrypted the whole thing. But because everyone
knew that their first digit was a 1, you would essentially know what everything is because of that one thing.
And that's why you use like GCM for symmetric crypto. Because if you just took AES, a block cipher, and just went through every chunk of your data, say it was an image, and encrypted it, what people have done is they've taken that encrypted data, tried to render it as an image, and you still see a fuzzy representation of what was there because you need to add that extra randomness and the proper algorithm. True security. So yeah, it's not just what you use, but how you use it.
Well, it's also for passwords, so like actually you don't usually just show the password.
No, you'd use Argon too.
So you can't just look it up in rainbow tables.
and like that's the rainbow table thing.
Yeah.
That's why you use solid or the knots that you were using. You have to sure you're using a 256
Yeah.
nonce, or you have the same problem with someone being able to come in with a rainbow table and then
breaking your encryption because they don't have to go through the algorithm.
Yeah.
They're just looking at the table for.
I didn't do too much on hashing in this. Maybe I do that as another talk, but like hashing is a whole different world. It's like 256 is great, but it's also designed to be fast. So when you're doing like a password, that's why bcrypt and Argon 2 exist, because they're compute and memory hard hashing algorithms, so that it takes effort to use them and to turn those bits into the other bits. So when a user is logging in, they spend a few extra milliseconds because it takes compute to do that and memory. That's fine. They should only do it once or twice if they miss their password. But if Sir Bad Guy is trying to figure out what that hash is, what the plain text is for the password, they need significantly more compute and memory to run it over and over and over and over again to try and build a rainbow table and find the answer.
Well, so essentially, you have to believe that all your code is open, right? Like you can't deploy anything someone can't, you know, decompile into what you actually have, right? So you have to be cautious about like combining things and, like you say, not understanding them, because you have to assume that anyone who's really interested in breaking in something will be able to, you know, debug your stuff without, you know, whatever, decompile your code and know what you're essentially doing, right?
That's why you don't roll your own crypto. It does. If you aren't using the acceptance standards and they, you know, somebody manages to decompile your code and figure out an easy way to break your handmade crypto, suddenly you're in a world of hurt.
Like they could open Ghidra and try and look through your code. That's still not easy. And if you're relying on encryption, if you're using a vetted standard, vetted library, you stand, even if they, like the math's the math. Decrypting your code isn't gonna help if the key's not there.
Right. But like with SHA, we believed SHA was a viable approach for like 10 years before someone realized you shouldn't be using SHA for encryption purposes. Yeah. So like, we weren't stupid back in 2000 when people were still using SHA.
When people were using MD5 and stuff for passwords, but we learned. That's why I say research for your application. It doesn't move super fast, but you know, within 5 years, the recommendation might be different. What library you should use, what algorithm you should use, how you should use it.
I do want to give Steve online a chance to ask this question, not to interrupt, but
I was just going to bring up, there are higher level libraries that help you use the right algorithm, pad your data, make sure you use the right nonce and use different nonces with every encryption and use them in the right way. Like libsodium is great, especially if you have to transfer these encrypted bits across platforms and different languages. Or Google has their Tink library, Tink, is very good too, especially if part of your encryption and just kind of, it helps you use the algorithms in the correct order, in the correct way, as well as kind of interact with your keyring and do all sorts of neat things without having to figure out all that yourself and do all that labor.
Mm-hmm. Yeah, and I would also point out in the experimental, the X crypto package, there's a NaCl, so sodium subpackage that has stuff for auth, message signing, and boxing that smooths some of it out and does pick some of the right answers for you. I didn't bring that up.
I can't remember the exact differences between the NaCl and the Golang or
like, there's a couple different libsodian nations too, but the NSCL in the crypto core package will get you a long way, but I think, not sure what the current state is.
And it's what very experimental and Go doesn't mean you can't use it, right? It means
Yeah.
Subject to interface change. So, yeah. Or bug fixes. Or bug fixes. So it's fine to use experimental and broad. Let's go for it. Anybody have any other questions?
I will say, if you don't know where to do the research or what reading you need to do, understanding what things you want to check, Word Utah Slack is great for asking questions. And there are several of us that have a lot of experience with this. We will have differing opinions that you could like read and pick from and explore, and it should give you a nice versing in the crypto space to do the right thing, you know, according to what you come up with and not what I say or whoever says. And so I think don't be afraid to ask questions. Don't be afraid to look stupid. This is a very technical area that a lot of people don't dive into. It's a lot easier than people make it out to be. And you can build some interesting things off of the standard tools that are also industry standard and or a little more granular than like a library that does magic black for you. So don't be afraid. Don't be afraid.
You don't need Vault,
Ask questions.
right? You don't need Vault. You don't need KMS. You don't need, like, these are all tools that have their value. Only be great.
Yeah.
That add value, but they're not strictly necessary if you want to transmit encrypted messages between servers. Like,
Yeah. I mean, you don't even need to like use a library for like, oh, I need an auth package. Like, you can actually roll your own auth pretty much in a very, very secure standard way. I have examples that I could show in Go and or Python, like just using off the shelf kind of primitives, but not a library that does all of it for you. And gluing those up is a few lines of code if you understand what the underlying pieces do. It's super, super easy. Just don't be afraid. Just ask. It'll be fun. This is good programming stuff.
I would echo that. It feels intimidating, but it's easier to use than it seems once you start playing with it.
we had so many crypto